This is a double physical pendulum. That is, instead of being the point mass that's shown quite a bit in vibration text, it actually has two pendulums, and each one has a fairly sizable moment of inertia. This model has aircraft ball bearings at the top, and I've forgotten who built it. It's a long time ago. This has two distinct modes of vibration. One is when these are swinging together like this, and then the second and higher mode of vibration is when the masses are going in those opposite directions. Now, the interesting thing about this particular vibration problem is that one can use that to illustrate the concept of coupling within the stiffness matrices. And for instance, if we take theta 1 as the displacement of the upper pendulum and theta 2 as the displacement with respect to normal of the lower one, we can actually have a physically decoupled model in that I can give the upper one a displacement without causing a displacement in the lower one. And similarly, by applying a couple here, I can give the bottom one a displacement theta 2 without causing a displacement in theta 1. Now, while we're speaking of pendulums, I will go to the next model, which also has 2 degrees of freedom, but they are laterally coupled by a very weak spring. And because this coupling spring is so weak, the two natural frequencies of this are very close together. The first and lowest frequency is when the masses are swinging in the same direction, like this, and then it has a second natural frequency in which they're swinging in opposite directions, or a 1 minus 1 mode. Now, because these two modes are very close together, it gives rise to some interesting events. If we excite both modes at the same time, I can get a beating effect between the two modes, and the two masses then will take turns stopping. This one will stop, and then this one stops, when in reality the summation of normal modes of this problem would indicate that we have beating between the two modes of vibration. Beats occurring, of course, when we have two frequencies that are close together. Now, here's a case where the masses are weakly coupled because this is a very weak spring. Now, I have another model in which the masses are strongly coupled, and it just indicates some of the curious motions that one may encounter in vehicles of all kinds when this occurs. I have a short pendulum up here, a long pendulum on this side, and a very, very strong coupling spring. Now, the same thing is true. They'll have a fundamental mode that looks something like this, and then they will have a higher mode in which the two masses are going in opposite direction. However, it's almost impossible to excite the second mode without exciting the first, and so you get some very strange jerking motion. This mass appears to stop, whereas this one just has a more or less a jerky trajectory. By varying the strength of the coupling, the length of the arms on the masses, a wide variety of couple motions can be attained. Leaving that, we'll go to a 3 degree of freedom pendulum model. And again, this one is weakly coupled with two weak coupling springs, 3 identical pendulums, and it will have 3 modes of vibration. The lowest is when they swing in the same direction. And then there will be a second mode in which the outside ones swing inward toward each other. And then there's a third mode, which is difficult for me to excite, but it's when the center mass is going in the opposite direction of the outer masses. Now again, if we give this an asymmetrical starting condition, then it is possible to excite all three modes at the same time, and the masses then will take turns stopping. You would note that this one stopped now this one stopped, now this one stopped. And it just shows that the effects of the strength of coupling between the systems and the interesting motions that can be arrived at. An interesting problem that works with this particular set of equations is when we have three frequencies that are not integer multiples of one another, and it's possible that the motion will look like band-limited, low-frequency random noise, when in reality it's the sum of three different sine waves of different frequencies that are not integer multiples or sub-integer multiples.